All right, let's take a look at Tuesday's assignment. Um, Started talking about limits with regards to infinity, and that can happen really two different ways. It can happen if your x's approach infinity, and we call that end behavior. And we know there from earlier in the semester there's different types of end behavior that we'll be reviewing. And then the other possibility is that your y's go to infinity. And one of those possibilities is that y's are approaching infinity. As part of your end behavior, you have a diverging function, and we'll get into that to some degree today, review that. Um, but the other possibility is that your x's are actually approaching a specific constant, and your y's are still going to infinity. We call those vertical asymptotes. And that's what a lot of yesterday's assignment was about. Now, you've already checked all of these, I would hope, because they're all in your course pack. I feel like some of you guys aren't really using all of these worked out solutions in the back of the course pack, because last week I noticed a lot of the homework didn't have the work shown, you know, properly with regards to notation and how how things were working. And if you were checking them as you went, I think you would have been able to make some pretty good adjustments. So you're really on your own for 90% of this journey right now. If you're not willing to check yourself as you go, it's gonna be really hard for me to help you until it's too late in most cases. So please check yourself as you go. Um, the first set of problems was uh, for these 8 functions using graphs and tables. Oh, these are mostly functions that cannot be, you can't do these algebraically to the most extent, because like on these problems, you're taking limits as you approach infinity. You cannot plug infinity into a function. Infinity is not a real number. You can't like plug it in for x. It doesn't make sense. And so you really do have to use pictures, graphs, right? Tables, and to some extent, on a lot of the analysis skills that we developed during the first couple months of the semester. And I'm going to try to talk through some of those ideas with you, I guess, through this instructional video. There was a question on this first set of 8, and it was problem number 3. So I do want to take a look at problem number 3 a little more closely first. Okay. Um, so here is the graph that we get. And I think that's probably the easiest way to do it is with graphs. You can use tables also. But remember, we're looking for 2 different limits. The limit as x approaches positive infinity, the limit as x approaches negative infinity. So it looks to me like as x approaches positive infinity, this graph is winding down toward the x-axis, okay? I think we call that a horizontal asymptote when it gets infinitesimally close to a horizontal line. So we have a horizontal asymptote to the right as x approaches positive infinity. And so that's the answer to part A. I know that on your, on your solutions, it just gave you the answer, right? It just said, 0. It just said that your y values are approaching 0. But if we wanted to write a full limit statement, and I do want you to start practice doing that because you're going to have to do that all the time in calculus, we would say that the limit of our function f of x as x approaches infinity is equal to 0. So we never actually make it to 0, right? But we get as close as we want. And since limits allow us to, in essence, make it to infinity, okay, we know that we can't make it there, but the limit says, if you could, this is what you would achieve. All right, so that's how you would write the answer to part A fully. Part B says, what's happening as we go to negative infinity. Well, that's a different story on this graph. If we go to negative infinity, the x values are going that way, and the y values look like they're going way down this way, right? And so I would say that the way that the second part of this problem, part B, would be written is as the limit of f of x approaches negative infinity, that the graph is approaching negative infinity. Now remember, you can't actually have a limit that's infinity. Limits are supposed to be real numbers, but when you talk about end behavior, you can describe limits with infinity, and when you talk about one-sided limits at vertical asymptotes, you can talk about limits as infinity. That's really the only time you're ever allowed to say that a limit is infinity, and what you really are saying is what direction it's moving. It's not really a value that it's equal to as much as it's a value that you're moving toward. But anyway, the last part of this was part C, and that asked, are there any horizontal asymptotes? Identify horizontal asymptotes. Well, we already did. This guy right here was a horizontal asymptote, and it was at 0, right? Now notice it was not an asymptote in the left direction. Okay, it was not an asymptote in this direction. But you only, need a horizontal asymptote to occur in one direction for it to be considered a horizontal asymptote. And in the right direction, we definitely did have a horizontal asymptote at y equals 0. So y equals 0 was the horizontal asymptote. Remember, the check is this right here. This is the test. If the limit as you approach infinity or negative infinity, right, is equal to 0, that indicates a horizontal asymptote. That's the definition of a horizontal asymptote. If your end behavior, plus or minus infinity, in this case positive infinity, is 0, or a constant, I guess, any constant, 2, 5, whatever. If it's a constant, it's a horizontal asymptote. So hopefully that explained number 3. Looks like I had some older graphs that had some tables included. You can see it's not as pretty with this picture right here, but it's the same idea. We're approaching 0 to the right and negative infinity to the left. But the tables are interesting because you can see that as my values are getting bigger to the right, my y values are getting tinier and tinier, approaching 0. And on the other hand, as my values are going in the negative direction, getting bigger, you can see that, by the time I get to negative 12, I'm already up to negative 13,000. So definitely a good indication of exactly what we just considered. All right. There weren't really any other questions in here. But I did want to bring up the fact that we can use end, the end behavior ideas we talked about earlier with these functions, even though these aren't rational functions. I guess actually number 4 is. This is a big topic we'll be talking about today, but number 4, when you see that the power of the top is bigger than the power of the bottom, we know it's a diverging function in the end behavior model. The EBM, right, and behavioral model is 3x cubed over x. Remember doing those, right? 3x cubed over x. So really that's just 3x squared, and x positive x squared, it looks like this. So we know that as x approaches positive and negative infinity for number 4, that this function is approaching positive infinity in both directions. Big topic for today. But you can do this with any of the functions, okay? Like number 6, even though we have an absolute value function on the bottom, the power of that is still 1, and the power of the top is 1. So you really get kind of like 2x over x. And so you're going to get more or less a 2, as your end behavior. Well, that's a constant. Now, I guess it would be 2 in the positive direction, negative 2 in the negative direction, because you'll get a negative over a positive. But you can still do these. Like, what's more powerful, sine, which just goes back and forth between negative 1 and 1, or x, which is just a line that goes like this? Well, in both directions, x is more powerful than sine. X is going to continue to positive or negative infinity, which means the bottom of this function in number 2 is more powerful than the top in both directions. And we know that when fractions have bottoms that are more powerful than tops, we collapse to 0. And so without even looking at the graph of number 2, we should understand that the end behavior should be approaching 0. And if we go and look at a graph, right, look what happens. Oh yeah, as I go back, I get a 0, and as I go to the right towards positive infinity, I get a 0. We actually talked about oscillating functions like that dampen a little bit yesterday. But let's jump to the next section, 9 through 16. I did have a couple questions in here, but these are really all almost the same problems. It really just comes down to remembering how we dealt with vertical asymptotes um, back in January and February. So these first 3, or actually 4, are just good old-fashioned rational functions. And we knew that rational functions ran into problems when there were zeros in the denominator. So this guy's going to have a problem at a 2, right? This is going to have a problem at a 2. This is going to have a problem at a 2. This is going to have a problem at a negative 3. This is going to have a problem at a negative 3. For number 9, it's a really simple transformation, to be quite honest. We have a normal 1 over x function, right? The reciprocal function, we call that looks like this. Okay, that's the normal reciprocal function. This transformation just says move everything 2 units to the right. This is the exact kind of question you might have had on your exam number 2 back in February. Boom. So we have a vertical asymptote, because that 2 in the bottom, that doesn't cancel, right? So that creates a vertical asymptote. It shifts from the y-axis over 2 units. And so this question is saying, what direction is your graph moving, right? What direction is your graph moving as you come in and see the little plus sign right here, right? That says we're coming from the right direction. We're coming in from the right. So as I come in from the right, it looks like I'm approaching up. And so the answer to this question would be positive infinity. Okay. Number 11 is basically as simple, because it's the same graph. It's just this time we've moved back 3, right? We've moved that vertical asymptote back to negative 3. So that's what it looks like. And this time it wants me to examine this as we move into negative 3 from the left. See that little negative right there? Yep, from the left. So as I move into this asymptote from the left, oh, this time it looks like I'm going down, doesn't it? So the answer for number 11 is negative infinity. Okay. Now I will admit that problems like 10 and 12 are just a tiny bit trickier. I still know that I'm going to have vertical asymptotes at 2 for number 10 and at negative 3 for number 12, because those don't cancel, right? When you start getting canceling factors, then they become holes, not vertical asymptotes, different type of discontinuity. But the 2 and the negative 3 for 10 and 12 still do not cancel, okay? But the X on top instead of a 1 changes the game a little bit. And so we have to be a little more careful about what direction it's moving. It doesn't necessarily just do its typical, um, you know, down to the down on the left side, up on the right side thing. Okay, and so here's, I mean, you guys should just graph these. Honestly, X over X minus 2. Let's do that one really quick. X divided by x minus 2. And take a look at that graph. And so it does look like it's still going up to the, as I approach it from the right and down as I approach it from the left, okay? But we could do this if we really had to. Here's what we would do. We would just say, okay, I know that as I approach 2, I'm going to be either going way up or way down. The only question is what kind of numbers do I get? So pick a number that's close to 2. This one wants me to come in, oh, the print on this is pretty bad. Let me double check it. Yeah, this one wants me to come in from the left. This is a minus, okay? So I'm coming in this direction. Now, I'm going to pick a number just a little less than 2 then, just a little, maybe right here, like 1.9. So if I put a 1.9 in, and you don't actually have to do the math, you just have to test the type of number you get. If I put a 1.9 in, 1.9 is positive on the top, but 1.9 minus 2 is negative on the bottom, right? I'm subtracting a bigger number. Now, technically, it's negative 0.1. So it's actually pretty straightforward. You're going to get negative 19 when you do this division. But all I really need to know is that a positive divided by a negative is a negative. And so if I put, even closer numbers to 2 in there, like, 1.999, and I do 1.999 minus 2, I'm going to get a positive on the top, but I'm still going to get a negative on the bottom, but it's going to be a much tinier negative, and it's going to give me a much larger negative value. And as soon as I know that these are negatives on the left side of this asymptote, that tells me all I need to know. It tells me I'm approaching negative infinity. And that's how, oops, I guess that was number 10, sorry. So, that's how you can do these without having to look at that graph. Now this says use graphs and tables. Go ahead and look at the graph, but if you really want to be getting through this using analysis, that's analysis right there. Understanding that, when I'm dividing a positive by a negative, it's a negative. On the other hand, if I looked at number 12 and I came into 3 from the right side, right? If I put a number just a little bit bigger than negative 3 and like negative 2.999, okay, that would be a negative on the top, and a negative 2.999 plus 3 would actually be positive. So see, this time it comes in and goes down from the right. We're not used to that. Usually it goes up from the right. So that's how you can kind of test them. If you graph number 12, you would see exactly that behavior. It would be going down because a negative divided by a positive is a negative. And I just want to make sure you guys believe me here. So why don't we go ahead and do that graph? 1 x divided by x plus 3. And sure enough, as I come this way, look at that. I'm going down, 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 down. Okay. All right. So let's move on to these bottom 4, and I would just graph them. For example, number 16, right, is a secant problem, and I have the graph of it right here. If you don't remember how to graph a secant, you basically graph a cosine. Cosine graph, which would look like this. And you make it go up from the maxes, down from the mins, and the zeros become the vertical asymptotes. And so we end up with vertical asymptotes at every odd multiple of pi over 2. The trick here, though, is that my asymptotes don't always have the same behavior. Okay, and that's where this can get kind of crazy. If I have like a pi over 2 or a 5 pi over 2, or the next one would be a 9 pi over 2. Okay, so like every other odd multiple of pi over 2, then I have a left behavior approach, a limit of up positive infinity, and a down behavior of negative infinity, right? If I come in from the left, it's going up. If I come in from the right, I'm going down. However, if I do the other multiples um, of pi over 2, so like negative pi over 2, uh, 3 pi over 2, etc. Now as I come in from the left, I'm going down. As I come in from the right, I'm going up. See how these are opposites depending on what direction I'm coming in? This one, as I come in from the right, I'm going up. But this one, as I come in from the right, I'm sorry, from the left, I'm coming down. And so the trig ones, because of their periodic tendencies, are a little trickier. Actually, tangent and cotangent aren't too bad because they are consistent with their shapes. They are strictly increasing or decreasing, so that helps us out a little bit. But secant and cosecant, boy, that those get trickier, and so I would look in the solutions guide about how you would describe those every other odds. But the good news for you is that I'm not going to throw a question like that on. I might say, what is this doing at a specific value like pi over 2, but I won't make you try to describe like every other odd multiple of pi over 2. That can be tricky. And that's kind of how you do those. 13 and 14 we actually did back in last week. That was the one where the greatest integer function is going to keep giving you zeros, in this area. But then when you get to the next jump, you're going to be doing ones over that. But you're going to have positives approaching integers. And then so it really depends on what side of the integer value you're approaching from. That's the big trick on that. Am I coming in from the left or the right? I mean, we can go ahead and graph it. It isn't, it's an interesting graph to look at. So if we do the greatest integer of x over x, we get a graph that looks like this. All right, so I'm just going to I think I'm going to go ahead and cut this one out so we can draw on it a little bit. And what we see is we see that as I come in to 0, in this case from the left, I'm approaching positive infinity. So that's a pretty crazy one. We would have to break that. But as I come in from the right side, I'm just approaching 0, right? As I come into 1 from the left side, I'm approaching 0. But as I come into 1 from the right side, it looks like I'm approaching 1. And that's where these are a little weird, and definitely it's helpful to use tables and graphs because you can't you can't go plugging those values in. All right, let's move on to the next section, which would be 17 through 22. This time, instead of horizontal asymptotes like we were talking about in problems 1 through 8, we're really talking about vertical asymptotes, identifying them. And remember, the definition of a vertical asymptote is if my x's are approaching some constant value c, and the y values are approaching plus or minus infinity, well, then I found myself a vertical asymptote. Now, we did a lot of work with rational functions and vertical asymptotes back in Unit 1, and so that hopefully really paid off, especially on problems 17 through 20. They're all rational functions. You just have to factor them, right? So like on number 17, you factor Um, x squared minus 4, you get negative 2 and positive 2. Neither one of them cancels, so they're both vertical asymptotes. So the vertical asymptotes would be at x equals negative 2, x equals positive 2. That's the answer for part A. Describe the behavior to the left and the right of those. That's where it would be more helpful to take a look at the graph. Now you could do the little test thing I showed you where you take a number just a little bit to say the right of um, 2, and you could determine that 1 is positive, and if I put like a 2.01 in here and square it, it's going to be just a little bigger than 4, so that's going to be positive. So I get a positive over a positive, so that means that on this side of the graph things are going to stay positive. Now if I flip that and put it like a 1.99 in, now the top is still positive, but now 1.99 squared is just a little less than 4, so when I subtract 4 I actually get a negative now. Positive divided by negative is negative, so that means we're going down on this side of the graph. And so you could do a little bit of analysis without having to graph it for part B, but I think since the problem invites you uh, to look for those directions, I would go ahead and use the calculator to confirm that you are seeing what you think you're seeing. Um, Looks like I have a picture down here of problem number 20. So let's take a look at that one. At the bottom, 2x squared minus 5x minus 3 does factor. It factors into 2x minus 3 times x minus 1. And um, so, it's probably going to be help us if we go ahead and write that out. Um, so 1 minus x. So I need 2x squared, so that's going to be 2x times x. And then I needed 3. Does 3 go here, here? I think it's going to have to go over here. I think I might have said it was 2x minus 3, but it's actually 2x minus 1. Or I'm sorry, plus 1. Because that gives me the 1 times negative 3, and then a negative 6x and a positive 1x in the middle, so that's minus 5x. So yeah, so we want to move it that way. So the big question is, does this cancel with one of these guys? Because that creates a hole instead of a vertical asymptote, and the answer is no. These are both going to be vertical asymptotes. This one's going to happen at negative 1/2, right? This one's going to happen at positive 3. And so at negative 1/2, I'm just going to kind of move these here, right? Negative 1/2, and then at positive 3, we're going to have asymptotes. So now the only question is, as I approach these, so, as I come in toward, we'll just call it f of x, right? As I come in toward negative 1/2 from the left, right? From the left, am I going up or down? We know it's got to be positive or negative infinity. The question is it positive or negative? And this is where you could do that little trick, but it gets trickier with the bigger polynomials where I plug a number in like, negative 0.51. That's just a little bit below negative 1/2, right? Well, negative 0.51 would create a positive value on the top, and then you'd have to figure out on the bottom, is it going to be positive or negative? I think this would be positive, this would be a negative, negative, that would be positive. So I think you're going to end up with a positive down there, which would indicate to me it's going up. But it's much quicker if you look at the graph. And I do have a graph here, so let's take a look at it. Ready? As we come into negative 1/2 the from the left, just like we just talked about, it is going up. As I come in from the right, it's going down. So I would write that statement as negative infinity. As I come into positive 3 from the left, positive infinity. As I come into negative 3 from the right, negative infinity. So that's how you track those end behaviors using those functions. All right. Number 21 and 22 were a little different because cotangent and secant. We actually just did the secant graph over here, didn't we? Didn't we do the limit as we approached pi over 2 um, from the right of secant? So why don't we steal this graph and come back over here and examine the vertical asymptote structure. Once again, this wanted you to find all vertical asymptotes. So this is the one where it gets tricky because you have to determine, you know, where they are. I guess maybe 22 was the one I was thinking was 16 back here. 16 is actually pretty easy because it just wants you to focus on one vertical asymptote, pi over 2 from the right. So that was negative infinity. That was pretty straightforward. But this is the one where it gets tricky because now we're talking about all of the vertical asymptotes. So this is one where you have to define them. It's odd multiples of pi over 2, but then some of them have behavior where you're going up, coming in from the right. Some of them have behaviors where you're coming in down from the right. They alternate. And so those are the ones I think are good to talk about, but I probably won't give you any problems like that because it is a little tricky to describe what's happening with those. All right. So if you're still struggling on 17 through 22, let me know, and I can work out some of these other ones more specifically, but mostly it just is what are the bad numbers in the bottom. If they don't cancel, they're vertical asymptotes. Like on number 18, there's going to be a negative 2 that makes a 0. That's going to be a vertical asymptote. On number 19, negative 1, that's a problem, isn't it? That's going to make a vertical asymptote. So last set was 23 through 28, and we're doing end behavior again. Notice that we're doing end behavior. We're approaching positive or negative infinities. And we have some polynomial functions, or at least rational functions to start off with. Then we get into some trig functions the rest of the way. So these are definitely good ones to kind of be able to use your grapher as you need to. But I can walk you through the analysis of these also. So let me try to help you out with that a little bit. What's happening? Let's call this, I don't know, alpha of x. I guess you could just call it y. So what's happening, you know, um, what's happening to y as x approaches positive infinity? Well, this function has what I guess we would call equal power, right? And so the further out we go, this is really just going to turn into a 1 over a 1. And that's just going to be a 1. We ignore that. And 2 minus 1 is 1. So this whole thing, the further out we go, is going to turn into a 1. This also seems to have equal power, doesn't it? So those are going to cancel and just give me a 1 over 1. So it looks like I'm going to be multiplying a 1 by a 1. And I should have end behavior in both directions, you know, of 1. So I could put a negative in here, and I think I would get the same answer. Now, does your graph agree with that? Another way that you could do that is you could actually, you know, get a common denominator here. So multiply by x plus 1 on the top and the bottom of 2, and you get 2x plus 2 over x plus 1 minus x. So I guess that would actually be 2x minus this 1x here would just be x. So x plus 2 over x plus 1 multiplied by x squared over 5 plus x squared. So what are we going to get? What are we going to get? We're going to get x cubed plus 2x squared over x cubed is x squared times x. X squared is 1 times x squared. 5x is 5 times x. And then 5 is 5 times 1. Right? But when I look at polynomials and I examine what happens as we approach, you know, infinity or negative infinity, I really only care about the power terms. And once again, we get a tie, and the coefficients are 1 and 1. And so just like I mentioned previously, we get a limit of 1 as we approach positive and negative infinity. The graph will confirm that. And so I I guess I really should. I guess I really should graph this for you. Um, but I don't want you to wait while I plug it all in. So I'm going to pause here for a second and go ahead and enter that just so you can see it. Okay, so I'll be back in one. All right, I am back, and as you can see, I entered this function from 23 in exactly as it was. So I didn't simplify it, I just typed it in exactly. Let's take a look at the graph. Bam. So remember that what we determined is that algebraically, through analysis, that this is going to have a limit of 1 in both directions. Um, Indeed, if I went in, and I'm going to do two things actually for you, okay? One thing I'm going to do is I'm going to go a little bit further out so that we can see um, the end behavior further than 10 and negative 10, okay? And then secondly, I'm going to add a horizontal asymptote at 1. And look at that. You see how, indeed, in both directions, we have that horizontal asymptote at 1. So this is just an indication of how this analysis is really accurate if you follow it through. It's the same type of analysis we used back with rational functions, okay? You could do that same thing on 24. Now 25, 26, 27, and 28 get a little bit trickier because of the trig functions involved with them. But here's the thing, you can still graph them. Now actually 26 and 26 and 28 you can actually break up pretty easily. And even 27, I mean, here's the one thing I want you to understand, okay? And this is something I talked about yesterday, and we're going to talk about it again in the lecture for today. And it's something you need to remember. In the structure of power, so far the most powerful function we have is by far the exponential function. Now, that's not the most powerful function that exists, but as far as in our class, that's as powerful as things get. And the weakest is the constant. So, this is the weakest down here is y equals k, which never changes. And then over here, y equals, say, e to the x is the most powerful function we have. Now, as I mentioned yesterday, y equals sine of x is basically as weak as y equals x because it's bounded. It's stuck between -1 and 1. So it really has no power. I mean, we could say it grows, but then it also shrinks, but it's limited to these very small values. And so when I look at this and I break it down, I say, well, you know what? The power on the top is 2x because this is really, really weak power-wise. And the power on the bottom is x. So the end behavior model of this is really just going to be 2x over x. I can pretty much just ignore the um, the sign of x. Okay, and so the end behavior is going to be 2. If you graph number 26, you're going to get a horizontal asymptote at 2. Now, let me break it down for you algebraically, okay? Because if I take the limit, I think it wants me to do this in both directions, right? Yeah, positive, negative, infinity. I'll just do one of them. So the limit of 2x plus sine x over x as x approaches positive infinity is the limit as x approaches infinity of 2x over x plus the limit as x approaches infinity of sine of x over x. This is really just the limit as x approaches infinity of 2. 2x over x is just 2. And this, by identity, is 0. And this is what we talked about yesterday. We talked about this graph. We know that as sine of x over x approaches 0, we get closer and closer to a whole at 1. So it never equals 1, but the limit approaches 1. But yesterday we talked about what happens as you go towards plus or minus infinity. And it's a dampening function that kind of has this shape to it. But it's getting closer and closer to 0. It's collapsing to the x-axis. And so that's an identity right here. This is just this is a substitution that we made yesterday in our example, okay? And then the limit, to finish the problem, right? The limit of 2 is 2, and 2 plus 0 is 0, which is exactly the same thing I told you if you evaluate end behavior, right? So this is weak. So this is weak. X squared is strong. What happens when you have something weak over something strong as far as a fraction goes? It goes to 0, doesn't it? And so this whole thing I can tell you right now is going to go to 0 in both directions. Graph it, and you'll believe me. Okay, this guy right here, um, this has a a degree of 1. This has just basically a constant because the sine x is weak. This has a degree of 2. So once again, the bottom overpowers the top. That means the further we go in these two directions, it's going to collapse to a big old 0. So on 27 and 28, I challenge you to graph those. If you didn't last night like you were supposed to, I challenge you to graph those and see the the graph collapsing to 0 as x approaches plus or minus infinity. In fact, I actually have this, looks like right here, number 28, from last year. And you can see that as the x's go to infinity, look at what the y's are doing. They're collapsing to 0. And I even have a chart to show that as my x's grow bigger and bigger here. Look at the disintegrating values of the y. So this was a long video, especially if you didn't need all these questions answered. So I certainly hope when you watch these, you jump around and just get the pages that you have questions on. I hope that um, that you're using these because it definitely takes time to put them together. Let me know if you have further questions. 3 o'clock today. Assuming internet service is up and running, and have a good Wednesday. Please watch the next lecture.